Hi, this is Dr. Goldstein. In my last video, I gave a very conceptual definition of what a limit is, and in this video, I am going to give you a more precise mathematical definition of a limit. So the particular limit that we're going to talk about is a limit of the form, the limit as x goes to c of f of x equals L. So this is in some ways the easiest type of limit because x is approaching a finite number, and we're saying that our limit also approaches a finite number. So what this limit means is that for all epsilon greater than 0, there exists delta greater than 0 such that if x is in this punctured interval c minus delta comma c union c to c plus delta, then f of x is in this interval L minus epsilon, L plus epsilon. So this part right here in quotes, this is what is called a formal limit statement. And basically, it's just what we mean by the limit as x goes to c of f of x equals L. Now, I am using notation that is consistent with Tolman's calculus book, but a lot of the time, if you see this somewhere else, you will see this punctured interval written as the absolute value of x minus c is less than delta and greater than 0. So this is the same as saying that x is in this punctured interval around c, where you do not include c, but you can go delta below c and delta above c. And then this interval statement here is usually expressed by the absolute value of f of x minus L is less than epsilon. So what that statement is saying is that the distance between f of x and L is less than epsilon. And what we're saying with the other absolute value double inequality is that the distance between x and c is between 0 and delta. Okay, so again, this is the formal statement. You may also see this definition referred to as the epsilon-delta definition of a limit. It's very standard terminology because we have this epsilon and we have this delta that appear here. Okay, yeah, and what are those? So that's what I'm going to be explaining a little bit better in this video, is what exactly this definition means and why does this match our intuitive notion of what a limit is. So in order to do that, I'm going to show you an explicit example. So here we are looking at the limit as x goes to 2 of x squared. And hopefully if you think about that for a minute intuitively, x is getting close to 2. And we say, okay, as x gets close to 2, what does x squared get close to? And hopefully you say, oh, I know that one. X squared gets close to 4 when x is close to 2. So that's our limit. Our limit is equal to 4. Great. If we want to write this in a formal statement, we would write it using the definition as for all epsilon greater than 0, there exists delta greater than 0, such that. Okay, so that part didn't change from the actual definition, and this is how this type of limit statement always begins. Anytime you have x goes to some c and your limit equals some number L. You'll always start off with for all epsilon greater than 0, there exists delta greater than 0 such that. But now we go to our definition and we start to plug in what's actually given in this problem. So we have if x is in this interval. So remember, in the definition, we had c minus delta comma c union c plus delta. Delta is still delta, but here in this problem, we know what c is. Here's our c. X goes towards c. So in our definition, we can write 2 minus delta comma 2 union 2 plus delta. Again, we're just taking what was written in the definition and replacing it with what's given in our problem. Okay, then the definition continues. Then f of x is in, and if we think back to what's in our definition, we had L minus epsilon, L plus epsilon. And so we look back at the problem that we're working on right now, and we say, oh, there's my L. So I have 4 minus epsilon and 4, whoops, wrong color. I have 4 minus epsilon and 4 plus epsilon. So I literally, oops, and we don't just have f of x either, right? We can say to ourselves, hey, in our definition we had f of x is in, so we weren't actually done yet. We had f of x is in there, and I look back at my original problem and I say, oh, wait, hey, here's f of x. F of x is x squared. So actually I shouldn't leave this as f of x there. I should say x squared is in this interval 4 minus epsilon to 4 plus epsilon. So again, we took our value for c, we took our value for L, and we took our function for f of x, and we just plugged it into the definition, and that gives us a formal limit statement for this particular limit. Now let's look visually at what this actually means. So here I have graphed part of f of x equals x squared, and what I'm going to do is draw a suggestion of an epsilon. So here I have this 4 plus epsilon that's a little bit above, and I have this 4 minus epsilon that's a little bit below. And the idea of this definition is, I say for all epsilon greater than 0, epsilon you can think of as sort of an error. And it's really an error from the value of the limit. So it's an error from L. And so I know that my limit's equal to 4, and so I take this little epsilon above and an epsilon below 4. Okay, so when I do that, I look over at the graph, and I say, well, this gets me about here, and this gets me about here. And if I drop that down to my x-axis, I get this little window around 2, and it goes here, and let's go, oops, we want to go the opposite way. We want to go a little bit inside. So here's the smaller one and the smaller one over here. There we go. So one side of this is going to be 2 plus some little bit delta, and the other side is going to be 2 minus this little bit delta. I'm going to show you a better picture of this in a minute. That's not just my hand-drawn scrawl. So the idea is, for every window, for every epsilon window around 4, so for every epsilon window here, I can find a delta window down on my x-axis, so that when I take those x values that are inside of there and I map them back up to my function and back over to the y-axis, I'll stay inside my epsilon window. And that's exactly what the second part of this definition means. If x is within this teeny tiny little delta window here, then x squared, the values of my function, are in this teeny tiny little epsilon window here. That's what those two intervals are telling me. So the idea is, I drew a particular epsilon there, and I can make epsilon as small as I want it to be. So I can squish that blue window around 4 as small as I want, and the idea is that it's going to make the purple window around 2 even smaller. And if I can do that, if I can make these windows smaller and smaller and smaller, then my limit exists. I've satisfied this formal limit statement. For all epsilon greater than 0, there exists a delta greater than 0. So can I find this delta? As long as that's true, then my limit exists. Okay, we are going to look at a Desmos graph. So if you're not familiar with Desmos already, it's a really, really useful tool. I am going to put the link to this particular graph in the description of this video. So you can go there, you can click on that, and you can actually play with the same graph that I am showing you right now. So here I have the function f of x equals x squared, and you can see that here's where I plug that in. So you can plug in whatever function you want into this graph. And I'm going to play around with f of x equals x squared because it's nice and simple. And we have a equals 2. This is the c value that we were using. This is where your limit actually goes. And so if I take that and I move it around, it's going to move, well, you'll see it a little bit better when I start plugging stuff in. Oh, here we go. So here's my x equals a, and you can see that it's going right through 2. And so if I take my value of a and I move it around, that value is going to slide a little bit. So I'm going to put that back at 2. Let's see, can I get it exactly at 2? No, I'm going to have to type it in. I want to work exactly at 2. Okay. There we go. Go away, box. I don't want you. Okay, cool. So we are working at x equals 2, and you can see that. That's that blue vertical line. And we know that when we plug that x value in, we get the y value, y equals 4. But what we're asking about with our epsilon, so I've just turned on my epsilon window, is as I take this window around 4 and I shrink it, can I make sure that all of my y values stay inside there? So I'm going to start with a big epsilon. I'm going to stay with epsilon. I'm going to start with epsilon equals 1, so I can go 1 above or 1 below. And then what I'm going to do is I have these red dots. Let me slide this blue window in and out, and these are my deltas. This delta window is this blue window here. And if I put it a little bit less. Ooh. Let me get it just perfect. Ooh, this is so tricky on this computer. Okay, there. If I have that particular value for delta, you can see that these 2 points, their y values are just inside, especially that top point. The y value is just under 5. It's just inside this orange rectangle. Whoops, and I just moved them again. I'm going to actually take the slider and slide that over. There we go. That's better. So for this epsilon, for epsilon equals 1, this delta, which you can see that delta is set at 0.225, this delta will get me inside of there. Now, if I take epsilon and let's cut it in half, let's set it to 0.5, that same delta doesn't work anymore because my y values are outside. My y values here are outside of the orange window. But if I slide them in, oops, let's slide that a little bit smaller. If I slide them in, again, you can see, and I can click on these points and actually see the values. You can see that those y values are between 4 plus 0.5 and 4 minus 0.5. So that's 4 plus epsilon and 4 minus epsilon, and the y values on the entire function in that blue rectangle, all of those y values are inside of the orange rectangle. And so theoretically, you can see that you can do this. Whoops, stop moving. Thank you. Theoretically, you can do this. Now, this only has so much fine-tuning that you can do. It's set to pretty specific parameters. Oh, but even here, look, I can make that delta window that small, and it looks like those values are inside of there. So the mathematical idea is I can make epsilon infinitely small, smaller than that even. and I can find a delta small enough that will stay inside of there. That is the idea of this limit. As this orange rectangle closes in around 4, I can just keep my x values close enough to 2 that all my y values will stay inside of there. Okay, so again, I am going to link to this calculator in the description so you can go play with it yourself if you want. But this is the epsilon-delta definition of a limit. So I'll stick that up here again. For all epsilon greater than 0, there exists delta greater than 0 such that if x is within delta of c, then f of x is within epsilon of L.